Here I'm going to show you how to use the Euler-Lagrange equation in order to calculate equations of motion for the following system. So here we have an inverted pendulum. So we have that consists of a particle P with a mass m that's attached to the end of a massless rigid rod with a length of r, and that rod can rotate about 0.0 here. In addition, we have a spring that's attached to the particle here, and that spring has a coefficient of k. In addition, the resting length or equilibrium position of the spring is going to equal x sub o, and so this x sub o is equal to the length of the spring when this pendulum is in this current configuration. Okay. And so from there, we define our reference frames. We're going to stick our fixed frame A here. So we have A1 and A2. And in addition, we're going to define our B frame. And this, how I've drawn it now, B1 is actually overlapping A2. And then we have the B2 vector there. And the angle between the two frames, so between A1 and B1, is theta. So to use the first step in using the Lagrangian method is to define our generalized coordinates. So in this case, this system here has 1 degree of freedom, meaning we need one generalized coordinate. And it turns out that theta is a very reasonable choice of generalized coordinate for us to use. In which case, then we're going to set Q1 equal to theta. And again, what this means is that we're going to get one equation of motion at the very end, and it's going to be in terms of Q1 and its derivatives. So next, we calculate the Lagrangian of our system. So again, that's L is equal to T minus B. So here we have, we only have one mass, so we have our particle P, and therefore when we're writing out T, our kinetic energy, we can write this simply as 1/2 m, and then this is the velocity of our particle in frame A squared. So that gives us 1/2 m, and this is our Q1 in the Q1 dot in the B2 direction squared, which then simplifies down to 1/2 m r squared q dot 1 squared. For the potential energy, so PE, well, first we define the reference height of our system, so where potential energy is going to equal 0. And in this case, we're going to put it right at where our ground is, right? So the height of 0.0 here. So when the pendulum has a theta of 0, it's going to have no potential energy. And right, so we can actually here I've drawn the pendulum at the state which theta is equal to 90 degrees, but I'm just going to draw it like this just to give you a quick reference here, right? So ultimately what we're going to need to calculate is for every theta value, what is this height here? So what's the height in the A2 direction? And that is actually equal to mgr sine of Q1, right? Or sine of theta. And in addition to our potential energy from our gravitational force, we also have to consider the potential energy from our spring force up here. So again, the equilibrium position is when our particle P is basically at the origin in terms of the A1 direction of our, so basically as it's drawn here, right? So this is when the spring force is exhibiting or exerting 0 force on the particle. And so we can think of our spring displacement as, let's take this orientation of our pendulum here, right? It's going to be this distance here in the x direction, because again, the spring can only apply horizontal forces. This is the displacement of our spring. And so we can write this as here 1/2 k, and then this displacement we can write as r cosine q1 squared. And we can just rewrite that all as mgr sine q1 plus 1/2 k r squared cosine q1 squared. And so to compute the Lagrangian, right, we subtract t from v, so our L is going to equal, so t is 1/2 mr squared q1 dot squared, and then we have minus v, so minus mgr sine q1, and then minus 1/2 k r squared cosine squared q1. And then we move on to our next step, which is to evaluate the Euler-Lagrange equation. So here we only have 1 degree of freedom, so we'd only have to calculate this once, and we can write this as d dt, and we have the partial of our Lagrangian with respect to q1 dot. Again, we just need to put the 1 because we only have 1 coordinate. And then we have minus the partial of our Lagrangian with respect to q1. And we can set this all equal to 0 because the system is conservative. Right, so again, if we come back and draw our free body diagram of the forces acting on particle P, right, we have a gravitational force, we have a spring force, and then we have a tension. And the only forces that are doing work are our spring force and our gravitational force. The particle does not move in the direction of tension, so tension does not do work. So we can come back over here and we can calculate each of these terms in order to get our equation of motion. So we'll start out by calculating the partial of our Lagrange, so partial of L with respect to q1 dot. So if we come up to our Lagrangian, we only have one term that has q1 dot in it. So if we take the partial derivative of that term, we end up with mr squared q1 dot. And then if we take the time derivative of that, so if we calculate this component here of our Euler-Lagrange equation, this ends up equaling mr squared q1 double dot. Next, we turn to this term here, the partial of L with respect to q1. And so there we have two terms to consider. So the first is this mgr sine q1, which if we take the derivative of that with respect to q1, this ends up being negative mgr cosine of q1. And then when we evaluate the partial derivative with respect to q1 in the second term, we use chain rule to calculate this, and we get the following. So I'll just write out each of the individuals. I'll just write out the solution from the chain rule, right? So we get 1/2 k r squared times 2 cosine q1 times negative sine of q1. And so what that simplifies to is negative mgr cosine of q1, and then we have 2 minuses, so that becomes a plus, and then the 2's cancel out, or the 2 and the 1/2 cancels out, so we get plus kr squared cosine of q1 sine of q1. And then we plug these terms into our full Euler-Lagrange equation. So we end up with mr squared q1 double dot. And then here we have minus this term, so this becomes plus mgr cosine of q1, and then we have, this becomes minus kr squared cosine q1 sine q1 equal to 0. And it turns out that, we can do one simplifying step, which is to get rid of one of the r's in each of these components. So we'll get rid of that squared and that r. So we can simply rewrite this as, m r q1, oh, that looks like a g, q1 double dot plus mg cosine of q1 minus kr cosine q1 sine of q1 equals to 0. And this right here is our equation of motion.